so this is the chemistry lesson video for section 16.3. So we are going to focus on something called colligative properties. So a colligative property is a property that depends only upon the number of solute particles and not the type. So it doesn't matter if you dissolve sodium chloride or magnesium chloride or lithium oxide. It doesn't matter what you dissolve into something else. It just depends on how much you dissolve. So the three colligative properties that we're going to talk about are vapor pressure depression, freezing point depression, and boiling point elevation. So depression means they go down and elevation means it goes up. So in other words, when you dissolve a solute in a solvent like water, the vapor pressure will get lower, the freezing point will get lower, and the boiling point will get higher. All right, and so the more you add, the more these things happen. So like if I dissolve salt in water, it's going to lower the freezing point a little bit. If I add more salt, it's going to lower it a little bit more, like that. So let's just go back over what happens when something dissolves in water. Remember, you had to draw a picture of this. All right, so when you have something like sodium chloride, those polar water molecules, remember they have that partial positive, partial negative side, they attract to those positives and negatives. And so our negative one is surrounded by the positive hydrogens. Remember, it's just a partial positive on the dipole moment. And our positive ions are surrounded by those partially negative oxygens on the water molecules. Okay, remember we drew them kind of as Mickey Mouse heads in our previous video. All right, and so this is what's happening when something is dissolving in water, when you have a solute. And so those water molecules, they are attracted to those new solute particles. So, vapor pressure depression. Vapor pressure is the pressure of a vapor above a liquid. So like if this is water, most of the water is going to be a liquid. Notice we have a lid on the container, but some of it will evaporate. Those evaporated particles are going to cause some sort of pressure. So the vapor pressure is what's caused by those particles of water that have evaporated. The vapor pressure decreases when solute particles are added to the solvent, because the solvent particles are attracted to the solute particles, so they do not want to leave the solution and become a vapor. All right, so what happens is these water, we'll just pretend like this solvent is water. It doesn't actually tell us what it is, but we'll pretend like it's water. So these water molecules, they're attracted to each other because they're dipoles, so they all act like tiny magnets. But they see each other all the time, right? Think about you and your friends at school. You see your friends at school all the time. So you like each other, you're attracted to each other, but you know, you see each other all the time. So then a new solute is introduced. So like sodium chloride or something like that is introduced. And so let's pretend like this is like a famous person who comes to school, these famous solute particles. You don't get to see a famous person every day. So are you just going to want to stand there and hang out with your friends, or are you going to want to go see the famous person? You're going to want to go see the famous person. And by the way, you pick whoever famous person you want to pick. I don't know who y'all like. I'm old, so I don't know any people that y'all like. So once the famous person comes, you all want to surround the famous person. So these vapor particles that are creating this pressure, they don't want to be a vapor anymore. They want to come back and surround those particles also. So if you notice, there's less particles that are vapor at this point, and so that makes less pressure. Remember, pressure is collisions of particles. The less particles, the less collisions. All right, so when there aren't any famous solute particles, we have a certain amount of molecules that will evaporate and cause a vapor pressure. But once we introduce those new famous solute particles, less of them want to evaporate and become a gas. And so that lowers or depresses the vapor pressure. Now, I know you're probably like, oh my gosh, we're going to have to learn 3 different ones of these. Well, yes, but the explanation is all the same. Okay, if you just listen to the explanation or even read it, it's the same for all 3. All right, so when a substance freezes, the particles must get into an orderly arrangement to form the solid. So think about when we talk about what happens when water freezes, it forms that honeycomb structure. All right, so think of it as them making rings. So it says the freezing point lowers because when a solute is added, the solvent particles are attracted to the solute, so they do not want to get in the orderly arrangement. So again, we have water molecules. We're making them colder and colder and colder, so they end up getting into that honeycomb shape and freeze and become ice. Well, if we have these new famous solute particles, is everybody going to stop and get in an orderly formation? No, everybody's going to rush and try to surround the famous solute particles. All right, and so that's what happens in the particles, like it would happen in real life. And so what happens is the temperature must be lowered to force them to get in that honeycomb shape if we're talking about water. All right, so that's why temperature depresses or lowers, because again, the solute particles, since the solvent is attracted to them, they mess up that orderly arrangement. And so freezing just takes a colder temperature. So the boiling point increases because when a solute is added, the solvent particles are attracted to the solute. Notice, this is in all three of the statements. The solvent particles are attracted to the solute, so they do not want to leave the solution and become a gas. So think about water boiling. It's almost like the vapor pressure, except we're at boiling point. So the boiling particles leave and become a gas. Well, if you have these famous solute particles, nobody wants to leave and become a gas. They're all attracted to those new, exciting, famous solute particles. So the temperature has to be increased even more to force it to boil, to break those attractions. All right, and so that is what happens with colligative properties. Remember, if I ask you to explain any of them, the solvent particles are attracted to the solute particles. That needs to be somewhere in your explanation. All right, so remember, the colligative properties are based on the number of solute particles, not the type. So it doesn't matter if we have sodium ions, chloride ions, ammonium ions, it doesn't matter. It just depends on how many you have. So the solute particles could be atoms, ions, or molecules. You must remember that ionic compounds will break into ions when they dissolve in water. So like if I said CaCl2, a lot of you think that's one particle. Well, it is in its solid form. I mean, it's a formula unit. But when you dissolve it in water, it's going to break into a calcium ion and 2 chloride ions. So you actually end up with 3 particles when we're trying to determine what's happening with colligative properties. Okay, so for ionic compounds, you got to be real careful to check on that. What's the easiest way to tell something is ionic? Well, you'll see a polyatomic ion in it, or it'll be a metal and a non-metal. You can always go back to your electronegativity chart and subtract if you want, but I try not to give you any that would need subtracting in this chapter. So it's a metal, which is something from the left or middle of the periodic table, and a non-metal, which is something from the right. 2 non-metals, which are 2 elements from on the right of the stair step, they are molecular and will not break apart from each other. So it says, which solution has the higher boiling point? Well, first of all, let's make ourselves a cheat sheet. The more particles you have, the lower the vapor pressure, the lower the freezing point, and the higher the boiling point. So these 3 things happen with more particles. All right, so it says, and so then if I said the opposite, so less particles would have a higher vapor pressure, a higher freezing point, and a lower boiling point than something with more particles. Okay, does everybody see what I mean? Like it's the opposite. It doesn't mean that when you have less particles, vapor pressure goes up. It just means that between 2 solutions, the one with more would have the lower vapor pressure and the one with less would have the higher of the 2. Both of them will have lower than the original vapor pressure. All right, so it says, which solution has the higher boiling point? The reason I put this over here is so we can look. Okay, well the higher boiling point means I'm looking for who has more particles, because that's what you got to figure out. Do you want the solution with more particles or the solution with less particles? All right, so it says solution A has 3 moles of magnesium sulfate. Solution B has 1 mole of aluminum oxide. A lot of you would look at this and say, I want the one with more particles. This says 3 mole, this says 1 mole, this says 3, so it's obviously solution A. However, that is not how you do it. Remember, ionic compounds break apart. So I have to look at it. Well, SO4 is a polyatomic ion, so I know that means this is ionic and it's going to break apart. When it breaks apart, I'm going to get a magnesium ion and I'm going to get a sulfate ion. You always keep polyatomic ion together. So I actually end up with 2 particles, magnesium and sulfate. So I take my number of moles and multiply it by the fact that I got 2 particles. So I really have 6 moles of particles. Okay, so because the MgSO4 breaks apart, I actually have 6 moles of particles in that solution. Now let's look at our 1 mole of Al2O3. Well, aluminum is a metal, oxygen is a non-metal. That means it is going to break apart. When it breaks apart, I'm going to get 2 aluminum and hydroxide ions. Okay, so remember we did this all the way back in chapter 11. Some of you struggle with it then. All right, so how many particles do I get in total? I'm going to get 5 particles. So I take my 1 mole and multiply by the fact that I get 5 particles every time one of these breaks apart. And so that's 5 moles of particles. All right, so we're looking for the one with more particles, and so in that case, it would be solution A. Now, I know some of you are like, well, wait a minute, I could have told us solution A by saying, well, there's 3 moles instead of 1 mole. Well, it doesn't necessarily always work that way. Okay, so you have to be careful of that. So here, let me show you my work real quick again, because I know it's on my PowerPoint. Look. All right, and so we get 6 moles for the first one, 5 moles for the second, so solution A has the higher boiling point. Like I said, I know some of you were like, I would have said A anyway, you would have accidentally gotten it right. It's not always necessarily who has the highest number in front. All right, so let's look at 2 more. So we'll look at the first one together, or if you're feeling confident, you can try the first one. So it says, which solution has the lower freezing point? So if I look, the lower freezing point is who has more particles. So we're looking for more particles again. All right, so solution A has 3 moles of N2O5. Solution B has 2 moles of CaNO3 All right, so first we got to look, is anybody going to break up? Well, N and O are both nonmetals, so it is going to stay together. So 3 moles times 1 particle is 3 moles of particles. All right, so for part B, we have a polyatomic ion. So this is going to break up into calcium and 2 nitrates. So we get how many particles? Calcium and 2 nitrates, we get 3 particles. So I take my 2 moles and multiply by the fact that I'm going to get 3 particles, so I get 6 moles of particles. So see, now that I broke it up, solution B actually has more particles, okay, even though solution A has the higher amount of moles, because calcium nitrate breaks apart, whereas N2O5 does not because it's molecular. All right, so you have to be careful of that. Look for either a polyatomic ion, because that will break up, or look for a metal and a non-metal. All right, so you try the bottom one real quick. I'll assume you've done that. Pause the video and we'll look at it together. So it says, which solution has the higher vapor pressure? Well, if you look, more particles has the lower vapor pressure. Less particles has the higher vapor pressure. So we're actually looking for who has the less amount of particles this time. And so what you may want to do is, like if you're working on a practice sheet or something, just write this next to the problem so you can keep up with, are you looking for more or less particles? All right, so because I looked for higher vapor pressure, I'm looking for less particles this time. So we have solution A and solution B. Well, in solution A, I can already recognize there are 2 polyatomic ions. So I know it's ionic, which means it's going to break up. So we're going to get ammonium ion, which is NH4+, and nitrate ion, which is NO3-. So we're going to get 2 particles. So I take my 1 mole times my 2 particles. So solution A has 2 moles of particles. Ooh, sorry, I'm getting kind of sloppy right here. All right, solution B says 1 mole of aluminum bromide. Aluminum's a metal, bromine is a nonmetal, so this is also going to break up. I'm going to get 1 aluminum and 3 bromine, or bromide ions. So that's a total of 1 aluminum and 3 bromide ions of 4 particles. So I take my 1 mole and multiply by the fact that I have 4 particles. So there are 4 moles of particles in solution B. Alright, so even though when we start, it looks like it's going to be the same, because it's 1 mole and 1 mole, once we break them up, then we can see they're not the same. Alright, so solution A has 2 moles, solution B has 4 moles, so since solution B has more, solution B would have the lower vapor pressure. But since it asked me for the higher, I want the one that has less, which is solution A. So hopefully you got that one right. Okay, so like I said, the important thing is, first thing you need to do is figure out, are you looking for more or less particles? And then don't forget, metal and non-metal break up because it's ionic, or if you see an ionic, a polyatomic ion, that will break up, but 2 non-metals will stay together, or more. 2 or more. All right, so section assessment. What are the 3 colligative properties? Well, the 3 that we talked about are vapor pressure depression, freezing point depression, and boiling point elevation. Number 2, what factor determines how much the vapor pressure, freezing point, and boiling point of a solution differ from the properties of the pure solvent? Remember, it's the amount of solute particles. The amount of solute particles. So number 3, would a dilute or a concentrated sodium fluoride solution have a higher boiling point? Explain. Well, if you look, higher boiling point is more particles. Dilute means a low amount of solute. I'll just put low solute. Concentrated means a high amount of solute. So who would have more particles? The concentrated. Okay, so the concentrated would have the higher boiling point, and our explanation is because it would have more solute particles. Because it would have more solute particles. Alright, so let's move on to our last one. It says an equal number of moles of Ki and MgI2 are dissolved in equal volumes of water. Which solution has the higher boiling point, vapor pressure, or freezing point? Well, first of all, because we're talking about these 2 same substances every time, let's go ahead and determine how many particles. It says an equal number of moles, so all we need to do is look at how many particles it breaks up into. So K is a metal, I is a non-metal, so it's going to break up into K plus and I minus. So we're going to get 2 particles. MgI2 is a metal, Mg is a metal, I is a non-metal, so it is also going to break up, but it's going to break up into Mg and 2 I's. So we're actually going to get 3 particles. Okay, so it says, which solution has the higher boiling point? Well, if I look, boiling point is higher with more particles. So who has more particles? MgI2. Which one has the higher vapor pressure? Well, with more particles, that's a lower vapor pressure. With less particles, that's the higher vapor pressure. So who has less particles? It is Ki. And which one has the higher freezing point? Well, with more particles, freezing point goes down. So with less particles, that would have the higher freezing point. And again, Ki has less particles. Okay, so the important thing to remember is check to see if it's going to break up into particles. If it's non-metals, it will stay together as a molecule. If it's a metal and a non-metal, it'll separate, or if you see a polyatomic ion, that's another way to tell it will separate. Alright, so hopefully you didn't find colligative properties too difficult because we don't do any of the math based on them. We just kind of look at what happens when those particles break up.